Here's what you do. Okay, you with me? Okay, let's say we want to calculate an area under a curve, right? Okay, this is an area that exists. I can prove it to you that it exists because here is the graph, right? There is the graph of the square root of 1 minus x cubed on the interval from 0 to 1. And in fact, I can even ask the calculator to do that for me. I could ask it to calculate the numerical integral from 0 to 1 and calculate, and it tells me that the answer is 0.841309. Okay? In 6 places. So would you agree that exists?
Yes.
Okay. And the question, there was questions, how do we do that on calculators? How do we do that on the calculators? Well, here's a good example. Here's a good example for us to use. Let's...
Is this handout for the stuff we're doing today?
Yeah, it is. Yeah.
Is this the super geeky way?
No, there's the super geeky way I probably won't get to today, but that's a TI-89 method, which well, you guys should hang on to this because if you go into math or physics, you'll probably get a TI-89. So hang on to these handouts.
So should we get one for next year?
I think they're pretty slick.
If you want to be cool.
If you want to be cool in a super geeky way, you probably want to get one.
Good luck with that.
Okay. Okay, so the question was, how do we do this on a graphing calculator? 2 methods. There's a non-graphing way. We can go to the math menu. We can go up to numerical or finite integrals, number 9.
Oh, math 9.
Fill it in.
Okay.
Fill in the blanks. Okay, so this would be 0.
What is it?
It's giving us the A and B, the limits.
0, 1,
Okay? Yeah, I'll put this over here. So we go 0, 1, square root of 1 minus x cubed. X, and that ought to look familiar. Right. Now, did you notice something there, though, that it took the calculator a while to think about that?
Yeah. But
Did you notice that?
No.
Okay, it didn't do that before.
Wait, just do it 2 times and let us compare.
Now, there's a reason for this. Now, I want you just when we did this stuff before, it came up with examples, came up with answers almost instantly. It had to think a little bit, right?
Wait,
To do this,
do it again. I want to see.
hold that thought.
maybe
Well,
it's
it's
just
just
the way. Okay, maybe it's just the way. This marble.
Yeah.
No, it's not. The calculator is thinking.
What is it thinking about? Would you look at that?
It's thinking about what we're going to talk about today. It really is. It
No,
really
it's
is.
not.
Yes, it is.
How do you know?
I know. I know the algorithm that it's doing.
Prove it.
Okay, the other way to do that is, by the way, you can go up here to y equals, and you could input that function, right? So, real quick, we could input the
So put the
function.
function in again.
Yeah, so we would just put it in,
So math 9.
turn that off. Okay, so that, what was that again? Square root 1 minus x cubed? Okay, and then if I just go, let's set the window to go from, how about from 0, or from negative 0.5 to 1.5. I mean, that's whatever you choose. And then I'll just go zoom fit. Zoom 0. There it is, right? And so now if I did area under the curve, I could just go second, calc, 7. And then it just wants the limits. Lower limit is 0, enter. Upper limit is 1, enter. And it calculates it, and that ought to look familiar. Okay? Is that a little different answer, though?
It's the same.
3.
Maybe next.
It's a little different, isn't it?
Wow.
Why is it different?
It's a little, yeah, I think it is. I swear that's a little different. Look what we had. Well, look right there.
Yeah, I want to know.
Okay, 841309.
Remove the cursor.
Move what now? Whoops, hang on. What am I doing? And I think I input that right. Square root of 1 minus x cubed. What's going on? Okay. There's a reason for all this nonsense. There really is. Now, which is the better answer? The better answer is not this one. Whenever you do something graphically on the calculator, it's going to do some approximations that are going to make it a little less accurate. For most integrals, anything else we would have done prior to this section, we would have had the exact same answer and it would have gotten it very quickly. But there's something going on here. This is a great lead-up. I'm glad it took a little while to pause. Boy, this is perfect.
You knew it would. You were just doing it.
Oh, well. Okay, so anyway, so here's the problem. Now, we got an answer for that. It was roughly equal to
0.84133.
okay? Roughly equal to that, right? So to get that, wouldn't we have had to have done this antiderivative? Right? Okay, here's the problem.
What the heck? You hurt yourself?
Yeah, they can turn it off.
Come on, stop shading.
Oh, really?
Yeah. Can't be done. It is that this function.
Why?
Not integratable.
It's not integrable. It is. Okay, there are some functions, and this is just a reality for us in math. There are some functions that for which there is no family of functions that act as antiderivatives. It's just the way it is. There is no function you could differentiate and get this answer to within a constant. It just can't happen. They're out there. They exist. There are other functions whose integrals or antiderivatives are so darn hard to take that they might as well not exist because we're not going to do it anyway, right? There's only really a handful of them at this point that we're equipped to tackle analytically. Okay. No, that's not what I'm saying. What I'm saying is, how do we deal without having to rely on some piece of technology that, what would we do if there was an airborne nuclear blast within 100 miles? All electronics would fail, and how could we do calculus then if we didn't have?
I'd be a little more concerned about the high.
Well, we all know. You'd be most concerned about calculus.
Wait, why would the calculator fail?
Well, because all the chips would be fried. All solid-state electronics would no longer work. So,
What about the applicants?
yeah.
No, but our applicants would be attacked.
Okay, but anyway, let's not digress too much. I shouldn't have probably brought that up. But the point is, the beauty of math has not to do with technology. It has to do with the symmetries and just the ability of us to do all this stuff symbolically. So how do we deal with this stuff if there's an example that's not only hard but impossible? How do we get, because there obviously is an area under that curve. How do we find it? Very good question, right? We can't rely on our trick anymore. And this is the part of, I remember seeing this for the first time thinking, oh my God, that's really kind of a letdown because there is no way to do it. There is no way to get a perfect answer. We can only get an approximate answer. But the good news is we can always control how accurate our answer is. Okay, so if we need it to be, well, we can't. We can't ever make it 100% accurate, but we could say this. We could say if I need the answer to within this many decimal places, or out to this many decimal places, I can get it. If I need it out to this many decimal places, I can still get it, but I can't get it out to an infinite number of decimal places. Yes?
So, well, You can't find it because you didn't define like the limits, right?
No. That's what I'm saying is, I can't do this. Remember, for me to do a definite integral using the fundamental theorem of calculus, remember what we do. We say that the integral, the definite integral of f of x dx from a to b equals the antiderivative evaluated at b minus the antiderivative evaluated at a. For this particular function, that doesn't exist. There is no antiderivative. So we can't use the first fundamental theorem of calculus. It doesn't work. Right? Hey, guys. Okay, so what do we do? This is, to me, this was a huge letdown because it seemed like there had to always be a way. I mean, I don't mean like I lost sleep over it, but it really did. It bothered me philosophically when I first saw this in high school calculus, when I realized that I can remember this, that there's a problem here that we can't do analytically. We can't get an exact answer, which just seemed terrible. Now, it turns out that in physics, no answer is ever exact, and so it doesn't matter. I mean, that's kind of the way the world works. But this isn't physics. This is math. In math, we ought to be able to find that area under the curve that we just saw, right?
So why can't you anti?
Because there is a class of functions for which they just don't
Why can't you
exist.
do it to that function?
Just because you just can't. There isn't one. There's just no you can prove it. It's a hard proof, but you can prove that function can't have an antiderivative.
What about it makes it so that you can't do it?
There's nothing I can point to and say it's that. It's just that here's an example of another one. Let me think now. Another one would be they're kind of random. Like here's another example. You can't do this.
How are you able to prove them on the other
Just
Sine.
memorize all of them. There's like 100 of them. Just memorize.
There's another example. Sine of x squared can't be done. There is no. As weird as that sounds, there is no antiderivative of sine of the quantity x squared.
Well, what if you put it on your calculator?
It's just. I know it's weird. There just isn't a function what this means now. It means whose slope is defined by this function. There is no function that does that. That's exactly what I said. I sat there and said, well, that can't be. It's impossible.
We have a function that, if it's obviously useful, we have something that is open.
Well, we could. You couldn't do it, though, is my point. You couldn't. It's not like it's just not allowed for us to use it. It doesn't exist. In any universe, there is no way that function can exist.
You don't know that.
Yeah, you don't know.
Really? You don't know that.
I think I do know that.
I bet you. Oh my God.
I don't either. It still kind of bothers me a little bit, but I just know it's the case, and I just know nothing to do about it. Another one is,
You never tried to actually solve.
I think we can do. There's some other, and there's some of them that are like the ones I gave you are simple. The ones that seem simple. Some of them look pretty hard. You kind of look at it and say, well, I guess I can see that. But those are simple. I mean, those ought to work. So what do? Well, we got to resort back to our numerical methods. We got to backtrack a little bit. Think about the work that we did in developing the fundamental theorem, right? We added up areas under curves, and we did that using rectangles, right? We added up the area under the curve by defining some rectangles, and then ultimately we just let the number of rectangles go to infinity, and that gave us an exact answer. Now the problem with this is, if we try to do that here, when we let the number of rectangles go to infinity, the math falls apart. You can't do it.
It falls apart.
I mean, it doesn't. You end up getting an intractable problem. You end up getting
Can
a.
you try it?
Well,
Just show us.
I can't really, because here's why I can't. I'll justify why I can't. I can't, but it wouldn't mean anything to you, because the argument of this is an accelerated argument of this sine function. The fact that it's a nonlinear function of a function. It's a function of a nonlinear function. Means that in order for me to add this up in a way that even makes algebraic sense, where when I try to plug in, if I use x sub I equals a plus I delta x, like we always did, I'm going to get something so terrible looking that we're not going to be able to deal with the algebra. Now, there's a solution for that. I could instead do something like this. I could say, let's let x sub I equal... it's going to be something like this. Let's see, it probably would be... probably going to be something like a
Alice close.
squared plus x. How's that going to be? Here's what it's going to be. I'm going to set up my delta x sub i's to look like this. It's going to look like b minus a over over I squared. B minus a squared over some weird like that, where I'm going to let the widths of the intervals be non-uniform. And you see that that makes things much more complicated. It's not worth us messing with it. Just trust me on this one. If we try to do this, it's going to blow up in our faces. It's not going to work, right? So we're not going to be able to use our prior techniques for getting an exact answer. We're going to have to set the number of n to be some finite amount, right? Now, if we're going to have to set the number of n, the number of subintervals, to be some finite amount, not infinite, do we really want to use rectangles to add up the area under the curve?
No.
Aha, we probably don't. We probably do not. And here's why we probably don't. Because, now, you'll remember back to our discussion before, we were able to be pretty blasé about this. We said if we have some function that's doing this, and I'm going to add up the area from A to B, right? The fact that I'm picking an interval in here that's got a certain width, the fact that that rectangle doesn't fit very well when I stack those rectangles up.
It never did, though. Why didn't we just use trapezoids always to begin with?
You mentioned
Okay.
it before, but you never.
Doesn't fit, right? We got a bunch of discrepancies there. Why didn't we use trapezoids before? Because we always had the ability to let the number of rectangles go to infinity. And rectangles are a very simple area to calculate, right? So it made sense for us in the past because we had such, we had that trump card, being able to let the number of subintervals become infinitely small when the number of them gets infinitely big, right? Why not just let it be a really easy area to calculate? But if we're going to be stuck with this dilemma that we're currently in, right, where we can't let the number of subdivisions go to infinity, then if we're going to have a finite number of these guys, we don't want to pick something inefficient like a rectangle. We want to pick something a little bit better. So circle is probably not a good idea. What kind of shape? Now, if I focus in on one of these, if I were to blow up this part right here, right, what I see is this function that's going up like this, and here's the top of my interval. What would be maybe a better choice?
A triangle and a rectangle.
Which makes a trapezoid.
No.
Right.
We just want a triangle and we don't separate. No.
Okay, there's my rectangle. Let's trade that out for a trapezoid. So that point intersects the curve right there. This side intersects the curve right there. And then when I draw that straight line, that matches pretty well.
Not perfectly, though.
It's not perfect, but it matches pretty well. Now, if we let the number of those get pretty big, you can see right away that that trapezoidal rule is going to much more closely approximate the actual area. Okay, now we can do this. I want to talk, first I just want to talk kind of qualitatively about this, because this is actually, to me, is a really interesting topic in math and in programming. When you get a problem like this where we've got to weigh the cost versus the benefit of using a different kind of shape to get more accurate area estimates for each increment, right? Now, even better than a trapezoid would be if I did something like this. What if I did something like this? What if I took the left boundary and the right boundary and the value of the function at the middle, and I fit that into, say, a quadratic fit? So I'm going to find the best fit parabola that's going to connect that point and that point and that point. Now that fits really well. Is it perfect? No, it's not perfect, right? But then if I do that, if that defines the top of each shape, then the areas are very accurate. But that comes at a cost, because those shapes are much harder to add up, those areas, right? And so where's the trade-off? Because ultimately, what your calculator does, when it calculates a numerical integral, even for a function that's known, a lot of times, it does something like this. it's going to pick an algorithm that's going to break up that area into increments and add all those up. So do you spend the processing power on the calculations of the individual areas and then not be able to have too many to add up? Or do you add up a simpler area like a trapezoid and let the calculator just repeat that algorithm many more times? That's where when people are doing things like electrical engineering and you're focusing on, say, circuit design, you're looking at the nanostructure of these new chips they're building. That's where you got to, people really weigh that stuff. And they look at, okay, now, am I going to heat the chip too much here? If I do too many repetitions, and that's the kind of stuff that they would do. They would do some mathematical modeling and analysis of how long it takes signals to propagate along the surface of the chip and what's the delay. And now there's even some quantum effects you got to take into account. I mean, all that stuff comes into play. And you're gonna tailor the precise algorithm that chip is going to use to add up areas under curves based on the cost benefit of one comes at the expense of the other. Where do you meet in the middle, right? And it changes all the time as chips evolve. The algorithms evolve too. Okay, and maybe we'll talk more about that later. I think that's really interesting. But back to reality here. So what do we do then with our problem? Well, we gotta add this up using a trapezoidal rule. Now, because it's getting so late in the year, I normally would draw a big picture and draw trapezoids, and we would come up with the trapezoidal rule in the same way that we came up with the rectangle, right, that we used before. I'm not going to do that. If you want to, it's in the book. You can read it. I would encourage you to take a look at that. But I'm not going to take that time. What I want to do instead is I want to just look at the results of that and how do we use it. Okay? And then now keep in mind, this is the easiest of our available choices. There's another rule, the one I described where the tops of the functions were quadratic. That's actually called Simpson's rule. And it's better. It's better, but it's harder to use. And you really don't use that in first year calculus, but you will use it later. Like on the AP test, they would never use Simpson's rule. They would use trapezoidal rule. Okay, but later on, and you get into higher level calculus, you'll come back and hopefully take a look at that. The trapezoidal rule amounts to this, though. If we want to do an approximation, the trapezoidal rule is approximated by this algorithm. It's equal to b minus a over 2n times this sum. Okay, we're going to write this a couple ways. It's going to be x sub 0 plus 2 x sub 1 plus 2 x sub 2 plus 2 x sub n minus 1 plus x sub n. Okay? Now what do you notice about that? And let's remind ourselves, what do all these things mean? X sub 0, x sub 1, x sub 2. All that means is this. X sub I is just a plus I delta x.
Is this on here, John?
Should be. Maybe not. That might not be on there. I may not have printed out the trapezoidal rule. I'll do that tomorrow. It's not on there.
Yeah,
There's an example, but it's in the book. Trapezoidal rule is definitely in the book. But the way I write it's a little differently than the way the book writes. So I'll give you some tomorrow with our version. And if we're looking at an area under a curve, really all we're saying then, if that's F and that's A and that's B, just remember that A is really just x sub 0, right? And then x sub 1 is right there, and there's x sub 2 all the way up to B is x sub n, and that's x sub n minus 1, right? So we've got n. We start at x sub 0, and then as we take steps of delta x along and cut our function up, the nth step is the last one, right? Okay, so this is the end of the first step, end of the second step. The beginning of the first step is 0, x sub 0. Okay, so now in our answer up here, though, notice that I double count all of the interior boundaries, right? X, the 1 through n minus 1, all are multiplied by 2. And where that comes from, and you know, if we had gone through this in more detail, you would have seen this unfold. But I can just tell you where that comes from is, when I add up these trapezoids, x sub 1 is going to act as the right edge of the first trapezoid and the left edge of the second. And so it actually shows up twice then in my area calculations. That's why the 2 is there. X sub n minus 1 is going to be the right edge of the second to last and the left edge of the last. And so it shows up twice. But of course, the left edge of the very first interval and the right edge of the very last interval only show up once, because they're only involved in each in a single calculation of area, right? And so that's why you get that double counting going on. We can write this a little bit better. We could write this as, let me grab that whole thing. I think it's a little better. I guess it's a matter of opinion, but okay, so let's do this then. We can probably make this a little bit better. How about if we just say, now this multiplier we're stuck with. But then in here, I could just add those two up separately. X sub a plus, or x sub 0, whatever you want to call it, plus x sub b plus 2 times, there's my 2, the interior sum, right? So 2 times x sub 1 plus x sub 2 plus all the way up to x sub n minus 1. Right? Okay? And I could even do a little better than that. Why write it this way when that's really just perfectly made for a sigma, isn't it? Yep. That's x sub n. So maybe I should write it that way. The x sub b is the same thing as x sub n, and x sub a is the same thing as x sub 0. Right? Because that's the start of my interval and the end of my interval. Okay? Sometimes you might want to, you're going to probably like to think of it this way, because those are the limits of integration, right? Those are the limits. We know that that's A and that's B, right? In fact, I could even call those, that's a better way to do it. What am I saying? We really should just call that A plus B, right? Start the left boundary of the whole thing, the right boundary of the whole thing, add those up, plus 2 times this interior sum. And this is the part that's going to look an awful lot like the stuff you did in the past, but it's easier. It's easier because look, we're just adding up individual pieces. We're not having to multiply those by delta x's, and remember that made it harder. This is a much easier process than what we did before. Okay. Here's all our delta x stuff got pulled out front. It's all in that b minus a over 2n stuff. So we could write this even a little bit better. Here's the last version. b minus a over 2n times a plus b plus 2 times the sum of x sub I, right? That's it. So that's our trapezoidal rule. Okay. Now let's use that so you can see it's not that big a deal. We can do this for any function. It doesn't matter what it is. Let's take the one. How about if we look at? Well, it doesn't matter. Doesn't matter. What's a good example? Let's pick one that's not too complicated. Let's take one right out of the way. Okay. So what if we want to add up? Good sum function. Yeah, we'll do that this one. Okay. Oh, oh my gosh! You know what I forgot to do? I'm sorry. I did forget one thing. These I have these up as x's, but they're supposed to be heights. It's f of all those. Hang on. So I got to change this slightly. These are all going to be heights of the function. So I got to rewrite the whole thing. Do you know? Okay. So those are all in there. That's supposed to be f of x sub 2, because those are the heights, right? Of course. I mean, I don't know why I was. And then down here, this is f of a times or plus f of b, the height at the left interval, height at the right interval, plus 2 times f of all that stuff. Okay. So let's look at an example. Okay. Let's look at an example. Let's rewrite. Here's our trapezoidal rule. So a trapezoidal rule equals b minus a over 2n is what we're going to plug in every time, times the quantity, the value of the function at the left boundary, plus the value of the function at the right boundary, plus the sum of all the interior values of the function. We'll call it the interior sum. From 1 to n minus 1, not n, of f of x sub I, which is always just going to be f of a plus I delta x, right? Okay. All right, so then what if we have the function, let's take a sine function where we're going to let n equal 4, for example. Okay. Let's add up the area under sine x from 0 to pi. Okay. Now, if I let n equal 4, what's the value of delta x?
Zero.
It's always, what's delta x always? What's a and what's b?
A is 0.
0.
B is pi.
B is pi. So if we're breaking this thing up into 4 pieces, then it's just the width of the interval, pi minus 0, divided by 4, right? So pi fourths. So there's delta x, right? So the prediction that the trapezoidal rule is making then is that this is about equal to pi minus 0 over 2 times 4 times f of a, so sine of 0, right? There's a, plus sine of pi, right? Plus 2 times all the interior pieces. Right?
Why is it 4? Sorry.
Yep.
Why is it n 4?
I just picked it arbitrarily. I just said, what if we pick n to equal 4? We have to pick n. Okay, now we don't know if that's good or bad. It's not going to be very good, I can tell you that. But if we pick n equals 4, we're going to get an answer that it's going to give us an answer. But then comes the issue, how accurate is that? Fortunately, there is a built-in formula for the trapezoidal rule that tells us what our error is, what our maximum error is. So we know how well we did every time. Oh, we're probably not going to get to it today. Let's see if we can just write this statement down, and then we'll pick it up tomorrow. So we get 2 times the interior sum. Now, there's only 3 values of that, right? We're going from n equals 1 up to n equals 4, right? So that means that in here, we're just going to get the values of, back here, this should have been f's. We're just going to have x sub 1, x sub 2, and x sub 3 because x sub 4 is our last one, right? We only made 4 cuts. So it's just the interior ones, the numbers between 0 and 4. Those integers are the only values that we're going to have to add up in that interior piece. Now, if we had picked n equals 8, all the integers between 0 and 8 would have included 1 through 7. We would have had more to add up. That's still a small enough number that we could add them up maybe manually. But what if we picked n equals 122? Then we're going to have. Then we got to use a calculator. We got to use some kind of an aid to help us make that huge sum, and that's where maybe a calculator comes in.
The higher the number, the more accurate.
Higher the number, the more accurate. Right. Exactly. So for us, in this particular example, sine of pi fourths plus sine of 2 pi fourths, so pi halves, plus sine of 3 pi fourths, 3/4 pi, and that's it. We plug that stuff in our calculator, and that's going to give us our approximation. Okay, that's just how simple.
Is this a big equation?
It is, and it's once you've done it a couple times, it's the same every time.